All right, I have a piecewise function here. The piecewise function is this rational function on the left side of 6 and at 6. And then if we move past 6, we get a straight line, 1/2 x minus 5/2. So in fact, we're going to want to graph this. And we want to discuss the continuity of this function. So when I think about the continuity of function, let's remind ourselves the definition of continuity. A function f is continuous at a point in its domain, A, if the function value at A is the limit. All right, so notice that you need two things to happen. You need the limit to exist and to give you a real number. And you need that real number to equal your function value. So let's think about when this can fail. Right, it fails in that situation because even though the limit exists, you get whatever that y value is, it's not equal to your function, right? Your function's all the way up here. So we need to avoid situations like that. That's a discontinuity. It's also going to fail to be continuous in that situation. Right there, even though your function exists and is equal to the limit from the left-hand side, it is not equal to the limit from the right-hand side. So the limit doesn't exist there. Right? You're also going to not be continuous whenever you have vertical asymptotes, right? Because your function doesn't exist, neither does your limit. So effectively, we just can't have any gaps in the graph. You're supposed to be able to draw a continuous function without picking up your pencil. So let's graph this function f of x and talk about the discontinuity. Now note, my function f of x is broken up into this rational function and this straight line. Now, this straight line is going to be continuous everywhere, right? It's a polynomial. I can plug any x value that I want into this, and it's going to give me a nice real number out. This rational function is made of a polynomial divided by another polynomial. So it's going to be nice and smooth and continuous, except where I might divide by 0, right? Because I'm not allowed to divide by 0. So in fact, that's where we start. Let's figure out what's going to make me divide by 0. X plus 3 over x squared minus x minus 12. I can factor that denominator as x minus 4 times x plus 3. And I see I get that cancellation, x plus 3. So this function is really no more complicated than the rational function 1 over x minus 4, except I do want to note that that equal sign isn't necessarily exactly true. Right, this is true except when x is equal to minus 3, right? Because this function does not exist at minus 3. You would be dividing by 0. This function has no problem at minus 3, right? So this equal sign right there is true for all values other than minus 3. So if I'm graphing this, let's look at, or I might have a problem at, or rather we have a discontinuity. At x is equal to minus 3. It's a removable discontinuity, which will show from the graph that the limit will still exist there. And then the non-removable discontinuity, the one that we weren't able to get rid of, x is equal to 4. Right? When x is equal to 4, then I have a problem. I have a big problem. So in fact, we have a non-removable discontinuity at x is equal to 4. Right? I got a vertical asymptote there. Let's see what's happening at, in fact, let's go ahead and fill in the graph around 4. What's happening to this function as I get closer and closer to 4? So my original function was x plus 3 over x squared minus x minus 12. Well, let's use the simplified version, 1 over x minus 4. So I can't directly substitute. Let's look at the limit from either direction. So let's look at the limit as x approaches 4 from the right of 1 over x minus 4. Now, if x is approaching 4 from the right, then that means x is larger than 4. And if x is larger than 4, then that means x minus 4 is positive. Right? So this fraction right here is going to explode to infinity, right? Because your denominator is getting smaller and smaller, but it's getting smaller and smaller while being positive. So it's going to explode to positive infinity on the right side of 4. Something like that. If I look at the limit as x approaches 4 from the left of my function, well, if x is less than 4, then I'm taking something smaller than 4 and subtracting 4, so this is now negative. But as x gets closer and closer to 4, then that denominator gets closer and closer to 0. The whole fraction explodes to infinity, but it explodes negatively, right? Because x is less than 4 there. So on the left side of 4, my function grows without bound, but negatively. All right, let's look at the other discontinuity at x is equal to 3. What's happening over there? If I look at the limit, let me switch colors. If I look at the limit as x approaches 3 of my function, let's use the simplified version. Here, I have no problem directly substituting. If I send x to, oh, sorry, not positive 3, negative 3. If I send x to minus 3, I have a minus 3 minus 4 gives me a minus 7. So I end up with a minus 1 over 7 there. So here, my limit does actually exist. So if I come over here and look at minus 1, minus 2, minus 3, my function approaches the value of minus 1/7. Right? We have an open circle there because the limit does exist, but my function does not exist there. All right, so everything in green on my graph, let me get rid of some of these notes. Everything on my graph in green so far is just the graph of this rational function, x plus 3 over x squared minus x minus 12. And I'm only supposed to listen to that rational function until I hit 6. So if that's 4, then this is 5, then this is 6. Ooh, bad artist. There we go. In fact, let's figure out what y value we're approaching right there. Let's look at the limit as x goes to 6 of this function. So in fact, we're approaching 6 from the left, right? So we use the function that's on the left side of 6. All right, so again, we're going to use our simplified version. The limit as x approaches 6 from the left, 1 over x minus 4. If I directly substitute a 6 in for that x, I get a 1 over 6 minus 4, or a 1/2. That's 0.5. All right, so this y value right here is 0.5. That's the y value that my function approaches as I get close to 6 from the left. And in fact, I do actually listen to that function, right? I listen to that function at the point 6. That's why we were able to just directly substitute 6 in. The function there is continuous at 6. But where else might my function be discontinuous? So we've already talked about the discontinuities of that first part. We know the second part is a straight line. It's not going to have any discontinuities. But the question is, maybe this function and this function don't agree at the value of 6. Right? Maybe I have this situation where this straight line approaches 6 from the right, and it doesn't give me that 0.5. Right? In fact, in order to make this continuous, I need to move that. Oh, I wish this would work. There we go. I need to move this down to where they agree, where the limit will exist. All right, so let's see what's happening on the right side of 6. If I look at the limit as x approaches 6 from the right of this function, then I should use the function that exists on the right side of 6, which is 1/2 x minus 5/2. This is a straight line. It's continuous everywhere. I have no problem directly substituting. If I send x to 6, then I get 3 minus 5/2. That's 3 minus 2.5, or 0.5. I get a 1/2. So no matter if I approach 6 from the left or from the right, I get the same thing, which means my function is going to look like this. So let's summarize. I have a discontinuity at -3. My limit existed, but it did not equal my function value. My function value does not exist there. I have a discontinuity at x is equal to 4 because my limit didn't exist. My function didn't exist, right? It was a non-removable, sorry. No, that's right. It was a non-removable discontinuity. It was a vertical asymptote. And then I might have been discontinuous over here at x is equal to 6 because this function and this function might not have agreed. But it turns out that I am continuous. The limit from the left gave me a 1/2. The limit from the right gave me a 1/2. And my function value at 6 was also equal to 1/2. So I satisfied this definition of continuity there. So this piecewise function, f of x, is only discontinuous at -3 and at +4. It's continuous everywhere else.